Okay. Good morning to everybody. Thank you to be here for this lecture. I would like to continue the lecture of last time. You remember, basic idea of recursive least squares. The topic is in the context of the identification. And this is a method, I would like to say, quite known. And in order to give an idea about this, I considered an autoregressive exogenous model. Autoregressive, I told you last time, and this means that the output is considered as an output itself, of course, but also as an input, therefore regressive. X reflects the concept that we have an exogenous signal, an input basically. Is typically didactically is the most used model in order to understand this kind of approach. We have AR because it's not always necessarily necessary to use an external signal, but of course in control we have an input. This means makes sense to speak directly on this kind of approach. Yeah, everything started from this let me say static least square, or classic least square. Let me say static. And at the end, you remember last time, starting from this concept here, the concept basically, this says that the output of the system can be seen as a linear combination of the previous output and the input. I mean, why is the output today? Why, let me say, why at time k? Why at time k minus 1 is the output yesterday, and u is the input yesterday. Now, the question is, why I didn't put the input today? Yeah, now I will answer this question here, because last time, do you remember, I assumed that this equation is valid, but the question is when is valid? Because why I didn't put here theta 2 multiply u of k? Because it could be that the output depends, or the output of today, let me say, depends on not only on the input of yesterday, but also on the input of today itself. More in general, do you remember, as I formulated last time, how long should I consider the window of the data which I have to measure? Because we can see here that it seems to be that today is a function, or let me say the output of today is a function of the output of yesterday and the input of yesterday, but it's an assumption. Why not for before yesterday or before yesterday? Or as I told you now, why not the input of today? Makes sense to ask. Yeah, now I will try to answer this question here. Last time, do you remember, I told you about a lot of boring calculations. We can find the material. Last time here, I corrected simple time. It was one word. Anyway, it's the corrected just this formal aspects. Yeah, do you remember last time we concluded here because the idea is to find this theta 1 and theta 2, which could be in general they change over time. I mean, could be variable, or at least during the transient variable, because look here again, if we want to model a system with this structure here, we will see which kind of system we can represent in this form here. We see in the dynamics, because today as a function of, or better to say, the output of today is a function of the output of yesterday and the input of yesterday. This means during the time, during the step, remember here, try to imagine k multiplied ts. We can see here, everywhere is k multiplied ts equal k, right? Because ts is given, is fixed. This means if everything changes over time, at least theta 1 and theta 2 will change over time, at least during the transient. But it could be that they change over time also during the steady state. It depends what we want to represent. Anyway, theta 1 and theta 2 are two parameters quite general. At the end of my boring calculation, last time, it just algebraic calculation, last time we have seen that we can use this expression here in order to estimate the vector theta, which included theta 1 and theta 2. Here, I change a little bit I translate the time. I mean, you can read here theta of k equals theta of k minus 1. This is just a formal aspect, which is just for it's more suitable during the calculation to work with this notation here. But anyway, it works for each k. This means you can reconsider exactly the expression which I told you at the beginning. The idea is to find theta 1 and theta 2, which are two components of this vector here, as a function of the previous theta 1 and theta 2. And we had this expression here. We calculate this expression here using this boring, let me say, algebraic transformation. Now, we can see here that this expression here is extremely important because, again, I have the vector theta, which includes theta 1 and theta 2, as a function of the previous calculated or identified theta 1 and theta 2, plus something which reflects in what I am measuring, we can see here, minus what in the output, what I identified as at the step before. In some books, we can say, we call this innovation. This part here, the name is innovation. Multiply this correction factor, which we can see here. I don't have time to show you this inversion matrix theorem. But of course, we can use, nevertheless, also directly this expression here. But this is a little bit more, let me say, useful, because we can include, we can see in this form here a little bit better some variations of this recursivity square. Which one? I will tell you. We can see here. I don't have time to go in depth on this today. But if you look at this expression here, do you remember we started our analysis considering to minimize this cost function. I don't know if you remember, I told you last time very quickly, but this belonged to another course. But in any case,
same functionality of the cost function that you use in PSO.
Yeah, but lambda is equal 1.
Always.
Always in the case of PSO.
Yeah.
In the case of PSO, yes. Also until now, if you look here, we have 1. Now there is a variation which we are considering this weighted, let me say, least square function, in order to do another kind of optimization. Do you remember in our static least square PSO at that time I introduced least square with a static least square. We minimize this function here with lambda equal 1. But also this expression here at the beginning with this solution here, we obtained with lambda equal 1. Basically, the least square, the classical least square. Here, the idea is, if I want, for instance, considering more important what happened yesterday with respect what happened before yesterday, this is a little bit an impossible idea to consider in a cost function which we have a factor which decrease over time. This just I give you some ideas. Of course, we can go in depth a little bit with theoretical aspects, but believe me, the unique thing we change is instead of one, we have this factor here, which could be typically could be seen here. The value is very small, but very sensible, very is extremely sensitive. The solution. This could be because in exponential, we can see here. This is a little bit, I give you the idea. We can also apply this method here, which we have already the solution in our project and so on. The idea of today is more than this variations of least square. It's not the unique one. It's not the unique one. In particular, it's not the unique weighted recursive least square or a least square method. I would like to insist a little bit in these 10 minutes, and then I have to stop for a meeting, and then we will restart. To discuss together the length of the window. At this moment, it seems, if you come back on our initial hypothesis, that I need to measure y. Look over here. yk minus 1, two outputs, at time k and time k minus 1, and the input at time k minus 1. This means I need a window with two elements. Of course, I measure input and output in this form here. This is what I measure. I have a software after, when we restart after, excuse me for today, for the meeting which I have the software which I upload in my study, so we can understand, we can repeat practically everything a little bit more concrete, what I explained this last time and today. Now, how I can choose this window? Roughly speaking, or intuitively, is not so, let me say, so difficult to intuitively understand how long and which one. I mean, if I consider here theta 3, which multiply uk, assuming that the output depends directly what I am doing today, we can see that I need nevertheless in a window with two elements, but I have to include also the input of today. Doesn't change the window, but change, instead of just u of yesterday, I have to include also u. And the criterion to see how long and which variable I have to measure is exactly the number of parameters which I have to estimate. Let me show you more in detail with an example in order what I am trying to explain. Look at the system here. For the engineer, it's easy to understand. I have here the system. For the engineer, it's easy to understand that everybody is are engineer. Anyway, this equation here is not difficult to be here to be clarified. I mean, the Kirchhoff balance, say U input equals R multiply the current plus L, which multiply the derivative of the current with respect to the time. If I modify in the sense, if I explicit the derivative of the current in this form here, we have the derivative of the current equals 1 divided L, which multiply this expression here. Now, why I am put it in this form here? I am put it in this form here because you remember, I don't know if I already told you in this course, but in my courses, this is the standard form in terms of dynamics. This means what change in terms of, you remember, we called the current the state variable because the current is, let me say, responsible or reflects, better to say, the energy in the system. We have the energy which can be, I mean, the energy in the sense we have two kinds of energy or three kinds of energy. The input energy, I put the input, the energy which I will dissipate here, but this is not exactly an internal energy, exactly like this, because here it comes from out, and here go out. In the literature, we say, oh, physically, the energy which characterizes the system is the energy I can, let me say, store here. No? If you think about the internal energy, what remain in the system, what could remain if I don't have R, is exactly what I can store in the inductance, no? Because of the coil of the practical system or the physical system which I have. Therefore, we try to explicit everything in terms, or to explicit the equation in terms of the variation of the energy, which is reflected by the variation of the current. I don't know if you remember my course in dynamical systems, also in the complementary courses. You didn't attend my class, you know. But anyway, it's easy to explicit everything in this form, everything, the equation which I have by using Kirchhoff in this form here. This expression here at this moment, I don't want to clarify for the student who attended my automation. It's clear what I intend, but it's not extremely important, this part here. Why that? We will see in the implementation eventually why could be useful, but from a practical reason, but not necessarily. Let me see. We can also avoid also this expression here, no? The Laplace transform of this expression here. Remain on this. If I discretize about the discretization I told you, I think in this course, this equation here in terms of with using the Euler approximation, I told you a little bit, or let me say, assuming this possible, not the unique one. Let me say, discretization method, I will obtain, if I plug in these three, let me say, position in the first equation. At this moment, we don't need to clarify this. I will come back later. I plug in, I will obtain this one. And from here, it is really an easy matter to calculate this. Basically, this expression here at the beginning of the slide came directly plugging in these three expression or the three positions here. The derivative is equal to this one in accordance with the Euler approximation, which you input is equal to you input k minus 1, and the current is the current k minus 1, assuming that Ts is inside, but we didn't put for notation problem. This is the new expression, the expression of the physical model in terms of discrete. The course is discrete identification and control. This is the expression of the discrete form of my continuous model. Look, now, practical consideration. If I compare this expression here with my model, we can see in let me say, in a synoptic, in a parallel form, we can see that minus theta 1, if assuming that y, our output equals current, once y of k, once y of k minus 1, we can see this parallel form. This means minus theta 1 is this expression here. Again, if y correspond to current and u input correspond to u, and theta 2 equals Ts divided L. I don't know if it's, just to compare. And here we have two equations and two unknown, because assuming that R, or better to say, assuming that theta 1, the idea is to find, let me clarify better, then I have to stop. Assuming that I have to calculate L and R, because the idea is I have a system, I measure the input and I measure the output. We will see now in which term, how far away in the past. I already told you. But the idea is to estimate R and L, identification of parameter. This is the problem. Probably I forgot to say at the beginning. But from these two equations, which came from the consideration which I did, it's easy to see that L and R is equal, as is expressed here, S divided theta 2, and R1 plus theta 1 divided theta 2. This means once I am able to calculate theta 1 and theta 2, but I am able to do, because we had this expression here. Now, in the second part of the lecture, I show you the simulations. And now we can understand intuitively why it could be used just in a window with two with two samples, in which I measure yk minus 1, two samples, and uk minus 1 without uk. Look at this expression here, or this system here, with this expression here. If you do the same, I will obtain now as discrete form this expression here. But look, because of the dynamics which I want to represent, which is a little bit different, we can see here the expression here, which can be written in this form here. If I explicit the derivative of the state, we need something more. We need also, we can see here, excuse me, we need also the input at time k. This means the length of the window is the same, but I have to consider also not only uk minus 1, also uk. But at the end, we have a different expression. I can nevertheless calculate C and R as a function of theta 1 and theta 2. But of course, the model is a little bit different. We can see here. This means depends on the dynamics, if I want to conclude with one word. I have to stop here. I will come back. I have to shut down. I have to close the Zoom, but I will come back after the meeting. Excuse me for this interruption. I don't know how much time will take, but then I have time until 20 after past 20 past 12. This means, excuse me for this interruption. You can stay here if you want. You can do round here around. You can walk. Excuse me for today. And yeah, we will go ahead with this topic here. And in particular, I have the software to explain or to clarify better some aspect here. We will see a little bit later. Ich denke, ist okay, ne? So. Aber ich weiß nicht, weil.